Okay, so we move on this. There is a final things I want to say about central. So we finished the motion in a central force field, let's say. But as you will see, if you keep on studying some physics, or probably you already discussed this within quantum mechanics, there is another point of view. I mean, we look at the two-body problems, okay, and we studied that, and that was exactly solvable. It was an interesting example. However, there is another setting in which central forces are of interest, and they have been studied, and is what happens if you have your central force field, okay, and instead of studying the motion of a single body in this under the action of this force, you study what happens if you send a beam of particles, right? Instead of, so you send many particles from infinity. They come closer to this central force, the origin of this central force, and what happened to this beam of particles? It's like a swarm, like, you know, they come in and they are scattered, they say, right, under the action of this this force. Okay, so that's an interesting problem because of the way modern physics developed, essentially by studying this kind of problems, right, as you are certainly aware. That is, we wanted to look at smaller and smaller objects, right? And if you see, one way to look at objects is through light, and essentially, if these are photons, right, this is what happens. You have light scattered of objects, and the scattered photons comes to your retina in your eyes, and that's the way you see objects, right? That's pretty much. But the ability to resolve small objects is bounded by the wavelengths of your light, right? Light is made of waves. We will see that next year when we study. In fact, they are electromagnetic waves, and you understand that if you have a wave, the shortest, the smallest distance that you can resolve is about the wavelengths of this wave, right? I don't know. Is this clear or? Never mind. But if you really want to go on smaller dimensions, you need something with more energy, and essentially you need particles. So you look at particles by means of other particles. That's essentially what the physics, I mean high energy physics, has done in the 1900s and now in this century. And you know that this is the way they discover atoms, for instance, right? The structure of the nuclei inside the atoms was discovered by this kind of experiment by Radford and the other people. So, I mean, this is just to motivate why we look at this problem. So what you expect is that they come in, and then depending whether this force is attractive or repulsive, say this particle will go like this, you know, this goes like, in this case it's attractive, and so this one will go like this, and the other will go like this, and so on and so forth. So you want sort of a formalism to discuss this kind of scattering. So this is called scattering. Right, like, and you can do that easily. I mean, you can have any kind of force, but it's easier if it's a central force. So it only depends on the distance between this component of this beam and the center from which the force originates. So think of an atom here, and then you you have a beam of electrons, and then you look where these electrons end up. And by noticing the deflection angle, okay, as a function of the energy, then you learn something about this force field, okay. This essentially is all there is to know about high energy physics. For instance, you know of this large Hadron Collider in Geneva. Have you heard about this? This is the largest experiment, ongoing experiment in the world at the moment. They have essentially something like this. I mean, it's more complicated, but the idea is the same. They actually, instead of having a fixed particle here, they have two particles colliding so that they sum up their energies. And then they look the way they come out. And according to the way they come out, they try to reconstruct what is the structure inside these particles, okay? And that's what the high energy physics has been doing for many, many years, okay? So how do you describe this kind of setup? Well, let's try. So I assume that I have a uniform beam here of particles coming from infinity, right? They come parallel. So it's like by uniform, I mean that the density here of particles is a constant, right? And then usually the flux density is called intensity, okay? So flux density. So I call this I because it's usually so what is this? Is the number of particles, right? Is the number of particles that cross a unit area in a unit time, right, essentially. So you should think that here you put your unit area, and then you count how many of these particles are crossing this unit area for a unit of time. Say, every second you have, I don't know, 1 million of particles of electrons crossing this area, okay? The old TV screens worked with the same thing. You had an intensity of electrons hitting the screen and lighting up exciting some atoms, then giving off some photons, and then you were seeing the film. Okay, so this is the idea of, so number of particles, your flux density per unit area and unit of time. Okay, and then, okay, so this describes the beam that is coming in. And then somewhere here you measure, so you have some intensity, some flux density coming in, and then you measure how many of these particles come out here. And this angle that we will define better in a second is called the scattering angle. That is by how much, say, this particle has been deflected by your field from the original direction, okay? So they were going that way, but actually when you measure, you find that that particle ends up here, and the angle between these two directions is called the scattering angle. And you see that this allows you to define the crucial parameter, the crucial function in this business that is called the cross-section. Have you heard this word before? Cross-section. What is the cross-section? So the cross-section for a given, say, in a given direction is a function of this solid angle, and is essentially simply the ratio between this quantity here, I'm sorry, the number of particles that you find here in this solid angle omega, so number of particles within solid angle omega, or better, well, omega, divide by what was coming in. So the flux density, what I wrote there, the incident flux density, Okay? So I'm describing this situation. And so let's try and be a little more precise about what's going on here. Usually so you see you have this uniform beam of particles, so the only variables is sort of the distance of a given particle in this beam from the center of the beam. This is a cylindrical beam of particles coming in, and this distance is called S, where S is called the impact parameter. They are just names. So you see that I can identify the particular component of this beam by giving the impact parameter. So for that given impact parameter, I have a certain particle, and that ends up there as a function of this scattering angle. Actually, you see that because of the symmetry of the problem, this impact parameter is related to what a quantity that you already know, that is the angular momentum. You understand, right? Because if you come in this way, you have zero angular momentum. Remember the problem of the comet about the sun. If you come a little off from this central direction, then you do have some angular momentum. So this impact parameter is related to the angular momentum if each of these particles have the same mass that I call little m, and it has some velocity v naught, then you understand that the angular momentum, by definition, of this particle at a distance s from the central beam is simply this, right? Because it's the vector product of these two vectors, but they are in this plane, so you get the angular momentum, the angular momentum. And this is, you can also, of course, usually you don't talk about the, we don't, right, usually you don't like to talk about velocity. It's much better to talk about energy, but the energy is just, I mean, these are, they come from infinity, so I consider them as free particles, so I just have the kinetic energy. Of course, then they get some potential energy as they get closer to the central force, but let's assume that the force goes down sufficiently fast that here I can consider my incoming beam of particles as free, then the kinetic energy is just given by that, and therefore I can also say that the angular momentum is just s, the square root of 2me, right? That is nicer because I like to identify this beam by the energy, essentially. I only care about the energy of this beam, and then I study how the cross-section varies with if I vary the incoming energy. You see, this is the other nice things about this approach, that I stay, so here is infinity, right? And here, in a way, is another infinity. So I stay very far away and assume that this force is not like Kepler's force that has the unfortunate feature that goes down like 1 over r. And what is unfortunate about that is that it keeps on going. I mean, even if you are infinitely far away in a galaxy, you know, like Star Wars, in a galaxy very far away, still, in principle, our sun has a small component even there, right? Because it goes like 1 over r. It never goes to 0, really. It becomes smaller and smaller, but never 0. We will see that that gives a problem immediately here, because you understand, well, we will see it. So usually in this kind of business, you have potentials, the potentials going down faster than 1 over R. Typically, have you ever heard about the Yukawa potential? This is a potential, you see, it's a potential that goes like some constant over R, so just like, but then is killed by an extra exponential like this. So this is nice, right, because it's the potential that goes down, and it goes down really fast because it's killed. You see, when R is larger than, say, 1 over alpha, then essentially this is 0, really. So for this kind of potentials, roughly you have a 1 over alpha region where you have this potential. And if you farther than this 1 over alpha, essentially you can consider free space, no potential. So in this situation, really here you just have a beam of free particles characterized only by their density, right there, and the energy. And the same here. So that's what is nice about that. You don't really want to know much about this. This is like a black box. That pretty much that's what it is. If you take a nucleus, this is essentially a black box, and then you stay very far away, and you don't go and look at the things. You just look what happened far away, where you know pretty much everything. And by looking at this scattering, then you understand what is going on inside this black box. So it's a very neat way of doing. L is the angular momentum. This little L. This is the angular momentum, right? Because you see, is this vector here, the velocity, cross the other one, and okay, it's pointing in this direction, but I'm just looking at the absolute value, not as a scalar quantity. Okay, so is this clear, or do you want to pursue that further, or you rather forget about this scattering? I think it's useful. So what else can I say? Well, I want to write, you see, omega, I said, is this solid angle, right? So a small solid angle, you remember how this goes, right? Is 2 pi sine theta d theta, right? This is a small angle and so I really want to find this sigma as a function of this theta that I call the scattering angle. And so what? Well, I have here the definition. So how many particles are in the solid angle? Let's put now d omega. So in this solid angle here. Well, it depends on I, right? It depends on the how large is the density, the flux, the incoming flux. So it must be 2 pi I. There is always a 2 pi because you have cylindrical symmetry, right, in the beam, and then spherical in the. You see, so I look how many are. So I'm looking at the d delta theta. So here I'm looking at ds, a small fraction of the beam that is between s and delta s. Okay, so there the number of particles is going to be the density, right? The intensity, the flux density that I call I, right? S ds. 2 pi because I can go all around. Okay, I don't know if it's like you have a picture in your book. It's something like this, right? It's like a ring. This is the delta S, okay, and it goes 2 pi around, and it goes with this symmetry toward the center. So that's the number of particles in this solid angle. So it's this part here. So these things must be equal to sigma, that now is just a function of theta. Well, you still have the 2 pi. So how many are here between the theta? Well, you have 2 pi sigma, still the flux density, so I. So that's nice because at the end of the day, it does not depend on the flux density. Sine theta d theta, right? This is just d omega. I rewrote what I wrote here in words. I wrote it using the symbols I introduced. And if I simplify around, right, common factors, I get that my cross-section as a function of the scattering angle is what? It's just this. I take everything on the other side. So I have sine theta. And here I have a derivative. This means that if I know the impact parameter as a function of theta or vice versa, okay, I can take this derivative, I plug in, and I found the cross-section. And the cross-section characterizes this process. You have a characteristic cross-section for different forces. Depending on the behavior in R of your central force, you expect to have a different cross-section. So that just so that you know these terms. So cross-section, scattering angle, impact parameter, and this is. Now we can try and apply this formalism to a problem that we already know, that is a central force with the potential V of R, and then we specialize for the Kepler's problem. That in this context clearly is not the Kepler's problem, but rather, I don't know, the Coulomb problem, because this is not I mean, you do have this also at the gravitational level, but it's, I mean, not on experiments that we can perform. Because as we said, the gravitational force is very, very weak compared to the electromagnetic force. So usually this was done with the potential in which the constant was given by the charges. Typically, you have, for instance, electrons and then protons, say. Okay? So let's try and do that. See, this is the way we found out how matter is made, right? Because you start with light. So you have a beam. You know, the light is made of photons. You must have read that somewhere. So you start, as I said, you start looking, but of course with light with a high energy, like X-rays, and then you start seeing how matter is made, right? You start seeing how the atoms are inside all kind of materials. Then you increase the energy, and then you discover that you have atoms, and you increase the, so from the point of view of the energy of X-rays, essentially atoms are point, right? So you describe the cross-section, and you see that the potential for that cross-section is the potential that is given by a very peculiar force field. That is essentially if you have a contact interaction. So if it goes like a little off, it goes straight. If it hits the center, it comes back, okay? So then you discover that the atoms are points. If you increase the energy, you start seeing the structure inside the atoms, and then you see that it's not quite a point, that you don't have just going through or coming back. You also have deflections, because you start seeing the potential that is keeping the atom together, okay? And there, they expected to have a sort of uniform, distribution. So, I mean, you know that the atoms was made of positive and negative charges because it's neutral. And the first idea that you may have is that you have, for instance, like a cake with the raisins inside, right? The raisins are electrons, and the filling is the positive charge. But this is not the way it is, because if you do this experiment, you look at the cross-section, you find this cross-section that corresponds to essentially a very hard nucleus, and then essentially nothing around, meaning that you have a nucleus and then the electrons going around, but essentially the distance, from an electron and the nucleus is a little bit like a planetary system, right? From outside, our system is essentially empty, right? With some small planet somewhere, and here is the same. I know that it's more complicated because the electrons are quantum objects, but essentially this is a good approximation. And then they start looking at the nucleus, and so maybe that was a thick ball made of something. But that too, when you start probing that too, it was essentially empty with some quarks and gluons around. Okay, so and that's the level at which we are now. Maybe there is a further level down. I mean, even quarks and gluons are made of some other stuff. People think supersymmetric stuff or some other. But you see, this is the way high energy physics has developed, by using this cross-section and increasing the energies. And of course, if you want to increase the energy, you need bigger and bigger machines. That's the reason why the LHC, that is this Large Hadron Colliders, is 20 kilometers long. Very big machine. So for us, so now I want to use what I know about the motion so let me redraw the picture. Let's see. So something like this. Let's see. I have two pictures. I'm not sure which one is the best. Maybe this. So here you have the center of this force field. This is the axis of symmetry for the beam. And you have a beam coming in, now from right, just to change. And for a given impact parameter, I have this trajectory, right, that would have gone straight if I didn't have this force. Let's assume that is repulsive. And because it is repulsive, the orbit is going to be something like this, right? It starts with this impact parameter, then somewhere is curved, and it flies off like this, okay? So we are back to, if you wish, the problem of orbits. It's just I changed the sign, is a sort of anti-gravity because it's repulsive instead. In fact, it's an electric force, so the electric force can have both signs. So I have this charged particle. This is the orbit. And so this goes off with some asymptotic direction that is this one, right? So this was the asymptotic direction, the incoming direction that is parameterized by the impact parameter. Then this curve goes off, and then eventually it goes beyond the range of this force, so it keeps on going straight. Remember, F equal ma. If there is no potential, there is no force, so things must move in a straight line. And and this orbit then is characterized by an angle psi that is what we call theta on last week. But now, since I call theta the scattering angle, I have to give another name to the angle. So the orbit is a function r as a function of psi, while last week was r as a function of theta. I hope, I mean, this is the reason why there are so many letters that you can switch. Because traditionally, the scattering angle is called theta, so let's stick to this tradition. You understand that psi is not theta, meaning psi is not the scattering angle, because the scattering angle, what was the definition of the scattering angle? Is the angle between the incoming direction and the outgoing direction. So in this picture, theta is this angle here, right? That clearly is not this angle here. But there is well, maybe I should draw it this way. Like this, sorry. I mean, I want to start from, so this is theta. So it's a different angle, but it is related to the angle with which I'm describing the orbit, because you see that essentially psi is also this, right? Because these two are parallel. And the problem is spherically symmetric. That means that this part of the orbit, remember, I mean, if you exchange theta with minus theta, the equation of the orbit was the second order derivative with respect to theta, so it doesn't change. So that means if this is psi, also this is psi. I mean, this half of the orbit is the same as the other half. You remember this? Okay. If not, I just remind you. And then you see that you have a nice, I mean, theta, the scattering angle, is the absolute value, if you want, but is pi, right, minus 2 psi. Just by the geometry there, right? So that means if I compute psi for my orbit, then I'm able to compute through this simple relation theta, and then I can try and compute the cross section. Okay, so we do that. What is psi? What is psi? Well, you just go back to your notes or to the textbook, and you remember we integrate the orbit, right? So in general, the theta that is now psi was an integral from the point of, from the minimum, that in this case is this, right? This is the R minimum, that is the closest point of approach in your orbit to the center of the force, to the infinity. So from here to the infinity, then there is a factor 2 because of the symmetry of the orbit, because of the symmetry of the problem. And downstairs, you had the usual term, 2m, the energy minus the potential, whatever that is, minus this effective term in the potential that is due to the angular momentum. So here I have, because the angular momentum is related to the impact parameter, you see that if I'm able to manipulate this integral, I do have the relation of psi as a function of s, the impact parameter, right? And then I can use that to put it here and find the cross section. So let's do that. You remember this formula, right? Or you do. So what is the energy? Well, the energy I discussed it one blackboard ago, and it's just for this particular particle coming in with the impact parameter s. It has some velocity that I don't, that it is what it is m2v square, and this velocity is the velocity at this infinity, right? Infinitely away from this potential. So let's put this symbol. And I also said that the angular momentum is just ms v infinity, right? I'm just copying the same formula. And through this, I rewrote the angular momentum as a function of the energy. So let's plug this in here, right? And write everything. So I use this to write my psi as a function of, so I write it here, psi as a function of the impact parameter. So I have this integral from R minimum to infinity. Then I have this R squared downstairs, so let's take it downstairs, R squared, then the square root. Then upstairs I have L. L is ms v infinity, so I have a s here, right? Then I have to write, so in other words, you always have s equal L divided by square root of 2me. So here I can write SDS, okay? Then I take it inside, and that simplifies some factors here. So you can check that you get 1 minus S square R square minus 2 mv infinity, the potential. So just plug this in here, collect outside everything, and then okay? So you see different impact parameter, you do the integral in R or in S. I'm sorry, here I want to keep the R. I don't want to do the ds. Sorry. You do the integral in dr, so for different s's you get different psi, and therefore different scattering angle. And that gives you the cross-section, right? So all we have to do, so now I can write theta as a function of s by using this definition, right? So that tells me that is pi minus twice this integral, okay? And you see that, so I can rewrite it. You can switch to the u variables if you want. It's up to you. I mean, r square 1 minus s square. And to go further again, like last week, we have to decide what this potential is. So let's do it for the Kepler problem. For the Kepler problem, so actually it's going to be something that goes like this, but it doesn't matter. It doesn't matter. It's taken care. This is taken care by the scattering angle. I mean, it's going like this, so the scattering angle will be on the other side. And is not really, as I said, it cannot be Kepler's problem because gravity is too weak. So this K that in Kepler's problem is g newtons times the mass of the sun or whatever planet is producing the gravitational field, is for the scattering of charges, say for Coulomb, is something like, so charges of the same sign. Then you have a minus that makes that repulsive, and say you have z prime e square. You know, z is usually called the atomic numbers, right? So it's the number of electron that you have, and then z prime, say, is the number of protons, but okay, it's just a coefficient. And then, actually, I don't have to do all this stuff in this case because I already did it last week together with you. That I already know what the solution is because this is the case in which the energy is larger than 0, right? And I have an open orbit that I call hyperbole. So I already know the solution. I already know that I have an hyperbole that is characterized by an eccentricity, remember, is always given by 1 plus 2e L square divided by, well, there is this k, so in this case, I get z prime e square. Or I can substitute with the impact parameter here, right? And this is also equal to 2es divided by z prime e square, no, e square. So this, I forgot the square. So I already know this because I did my homework for the Kepler's problem, so I can just adapt and I don't have to redo this integral. I already know that the solution is a trigonometric function that describes an hyperbole, and I can just write this solution. I know that 1 over r, I put it, well, 1 over r is equal to that constant that in this case is just z prime e L square, the eccentricity cosine of well, here is going to be cosine of psi minus 1, right? So what is this when I go to infinity? You see, that gives me a nice relation between the angular momentum or the impact parameter, depending on what they are, and this psi that I need to compute, right? Because if I go to infinity, this goes to 0, right? And then I get, I mean, also this must be 0, so that means that the cosine of psi must be 1 over the eccentricity. So for the particle to be on that particular trajectory, I must have that 1 over the eccentricity is exactly the cosine of psi, right? And now I can go from psi to theta again using this formula, because you see that if the cosine of psi is equal to the sine of theta half. Right? Because you see the psi, forget about, let's assume that the signs are such that this is positive. So psi is pi over 2. Psi is pi over 2 minus theta over 2, right? Then you take the cosine, and the cosine of pi over 2 minus theta over 2, either you remember or you go to that famous book that I already mentioned several times, you get that is the sine of theta over 2. So that's it. I mean, I have, you see, I have the scattering angle as a function of psi, and I know that for this orbit, the cosine of psi is nothing but 1 over the eccentricity. So because I already solved this equation, I don't have to do this integral again. But this you must know, because what I'm writing here is only true if this potential is 1 over r. For a generic potential, you have to do the integral again, and you will find a different orbit. But for our solution that we already worked out, we already know this solution, so we have all we need, that is this. And now we are almost ready to write the cross-section. So now I erase this, because I already solved the problem. And I only want this. So you see, I want I have s sine theta ds d theta, right? So I need s as a function of theta, right? Now here I have sine theta half equal 1 over the eccentricity that unfortunately I have erased. The eccentricity was, you remember, right? 1 plus, well, let's write it in terms of the, so E square is 1 plus 2Es z prime E is square, right? So I have sine is equal to 1 over epsilon. So I want to write the, I want to turn it around. So that means, so I take 1 over and I square. So I get 1 over the sine is the cotangent square of theta half, okay? Well, is 1 plus the cotangent square, right? So this is e square minus 1. 1 over the sine square of an angle is 1 plus the cotangent, right? No? It's too late in the day for that. I mean, is the... Well, you check it. Because you add and subtract sine square, cosine square. That is 1, so you get... is always the same trick. So you see, this is nice because, okay, that I know, right, is just 2es z prime e square, okay? So in other words, the cotangent, I can take the square root, the cotangent of theta half is just equal to this. What I really need is s as a function of theta, so I take everything here, I multiply there, and I get that s is just this z prime e square divided by 2e times the cotangent of theta half. Now I can take this result and plug in here. I take the derivative and I have my cross section that is equal to what? Now the derivative of the cotangent is the cotangent divided by the sine square. That's what it is. So I leave it as an exercise to check that this is 1/4, this coefficient. So you have s times the derivative, so this coefficient square. One divided by the sine to the 4th. You have a sine here. You rewrite it by using the usual trigonometric formulas, and everything depends on the theta half. So this is the cross-section as a function. That's a very famous result. Is due, well, the first guy who wanted to compute these things was Radford in England, and he was exactly the guy who was firing electrons on atoms. And instead of seeing a uniform deflection, saw something like this, that essentially you get that most of the stuff goes a little deviated, and then sometime it just comes back to you. That's a very surprising result if you think that the atom is a sort of a uniform distribution of matter, but very reasonable if you think that there is a hard nucleus and then essentially very little around. And he was so surprised that then, you understand why this is surprising, because if you have a proton here and an electron going around here, that's perfectly fine for explaining this cross-section, but you see the problem that you have a charged particle moving in a circle. And since I hope I convinced you last week that contrary to the ancient Greeks, that they thought that if you go in a circle, that's the natural motion, for us, if we see something going in a circle, we know that is accelerating. And charges accelerating irradiate. So this system means that this electron is giving off radiation. And if you give off radiations, you are slowing down because the energy is conserved. So this system cannot be stable, and in a nanosecond, it will just collapse, and that will be it. There will be no. We will not be here, right? No ICTP, no Trieste, nothing. So that was the puzzle. On one hand, they had this nice result telling them that the atoms must be like that. On the other hand, they had Maxwell theory telling them that it could not be stable. So this was a puzzle, And that, of course, is the puzzle that gave rise to quantum mechanics. Final words about this. Well, I've been a little slow. If you take the integral of this, you see, this is the differential cross-section, it's called, because it's the cross-section as a function of the scattering angle. But nothing can stop me from integrating this quantity. This is called the total cross-section. That means the total cross-section because I integrated over all the possible angles. And as I already told you, if you take this integral, you see this diverges. So you have an infinite cross-section, an infinite total cross-section. But this is not a mistake. It's simply the fact that this potential that we use here goes like 1 over r. So no matter how large your initial impact parameter was, you still get small deflections. And when you pile up all these deflections, you always end up with infinity, right? It's a logarithmic infinity, but still is an infinity, meaning that it's the sum of an infinite number of pieces getting smaller and smaller, but not smaller fast enough to make a convergent series, so to speak. Okay. So, okay. If you wish, this is a technical problem that you have a total cross-section that is infinitely large. This result is due to, well, it was used by, and then it's named the Rutherford cross-section, Rutherford. He was a New Zealander working in England before World War I. Okay? So that's, I'm sure that now I told you more than you wanted to know about this, but okay. I hope at least you remember this cross-section and this scattering angle, and maybe we have a homework on this too. We'll see. Is this clear, or so probably you don't care much? You just want me to move to the next subject. But okay, if you then decide to do high energy physics, I mean, this is really going to be relevant for you. Otherwise, maybe not that much. So what is the next things I want to tell you? Well, we have a choice, but okay, I'll decide for you. So we have two. If you remember my first day, I said that I wanted to discuss in some detail 3 problems. One was the Kepler's problem, that's done with this little coda. And then we had the rigid body, the motion, that's a very interesting problem, but I postponed that to next week. And first I want to do a little about what I call small oscillations. Now this is really a very important subject, so let's do it so that I'm sure that we have time enough to it's not very long, but it has to be done properly. And if you wish, this is very important everywhere in physics. Why? So you know, so the problem of small oscillations are, as you see, a small oscillation. And they are, so why is this so important? As I already mentioned, this is very important because it's based on the harmonical oscillator, and that, as Kepler problem, is a problem that we know how to solve exactly. And these are very few. As I said, I think there are 4 or 5. Well, it depends what, but essentially there are very few. There are very few problems of which we know, contrary to what people think, that physicists know the solutions of all problems exactly. We know the solution essentially, well, you know the solutions of only 2 problems. That one is the harmonical oscillator, and the other, I just taught you last week, is Kepler's problem. Okay, so these are the only 2. And it's not that going to quantum mechanics you are learning new, because the Bohr atoms is the Kepler's problem. It just happened to be soluble, and it's the only one. And then the other is the harmonic oscillator, so no progress there. So, I mean, what we knew, we still know. And there are very few other problems that you don't need to worry about, that of which we know the exact solution. But these two for sure. So that one we discussed, and I'm sure that you already have used it in quantum mechanics. And the other one is essentially the harmonic oscillator. So why is the harmonic oscillator so important? Because we know the solution, okay, clearly, but also because if you consider an arbitrary potential, so let's consider a general problem that depends on some generalized coordinates, to use our Lagrangian formalism. Let's think for a second in one dimension. That is nice, and we can draw on the blackboard, because if it's two or three-dimensional, you have to wave your hands all the time. So it's one-dimensional, so I only have one generalized coordinate, and this is an arbitrary potential. So in general, of course, I don't know. I write my Lagrangian equations, I don't know the solutions. I mean, it's going to be a nightmare, a very complicated differential equations of which I cannot look in this book and find an integral. No, you look, it's not there. You try Mathematica, nothing. It just says, we don't know. It just returns the same function. So you're done, right? And this, of course, is 99% of the problems. But now think for a second and think that your potential has some equilibrium point. Okay? This is very often your potential, I don't know, it's going to be some weird stuff, but it's going to have some points that are equilibrium points, because the derivative, the first derivative vanishes and the second one is positive. And if you look at the system near one of these equilibrium points, you know that you can do the nice Taylor expansion, right? That tells you that the value of this function is going to be, so let's call this Q naught, is going to be the value of this function, right, plus the first derivative Taylor is telling you, but this is an equilibrium point, so the first derivative is not there by definition. So you only get the first correction, that Taylor's is one half of, say, the distance. So you are computing the potential here, a Q, so is some constant, right? And this constant is the second derivative of the potential computed in this Q naught point, right? Times the distance between your point and the equilibrium point, square. And then, of course, you have an infinite number of terms, but okay, let's... So you see a very remarkable things. Remember, this is a constant, and as we already said many times during the problem sessions, I can always shift my potential by a constant. So by all practical purposes, for all practical purposes, this potential is equal to 1/2 a constant times simply the distance from this, plus, okay, some other terms. And this is very good. It's a very good approximation if this distance is sufficiently small. And that's where this small comes in. For small oscillations means that I'm moving about an equilibrium point, but the amount by which I'm moving away is small enough that I can trust my Taylor expansion to be a good approximation up to the, by retaining only this term here. And I can neglect this stuff, this infinitely sum here, because this distance is small enough that this, this goes like q to the cube, q to the fourth, so they are suppressed compared to this. But now you see the power of this, because now let's write the Lagrangian for this. So this is an arbitrary potential. And the only assumption I'm making is that instead of looking everywhere, I look close enough to an equilibrium point such that my potential is well represented by this approximation. Now I write the Lagrangian. So we are in one dimension, okay, and with a single coordinate. So let's call this coordinate x, or if you want, let's keep it q. But let's call it, let's call the distance x, because this is handy. Now, this distance is my generalized coordinate, this difference, okay, and is a single particle. I put here a particle with mass m that is moving in this potential, but it's not moving everywhere. It's moving around this equilibrium point, and I'm studying small oscillations about that. So my Lagrangian is very simple. I have my kinetic term, and then I have my potential. But what is the potential? Minus the v of x. So I'm minus k over 2 x squared. And of course, when I see a Lagrangian, immediately I cannot stop myself. I want to write the Lagrangian equations, right? And what is it? It's just mx dot dot. This is the d dt dl dx dot, right? And then I take the potential. I take the derivative of the potential, so I get plus k x. Equal to 0. And you must recognize this equation, I hope, because if I take the mass here and I call this ratio omega square, this is this very famous differential equation that you must have seen many times. This is the differential equation for the harmonical oscillator, right? Where omega is the square root of k over m. This k could be if you study a spring, this is the strength of the spring. If it's something else, it's something else. But this could be the pendulum, because also the pendulum for small oscillation is described by this equation. Anyway, whatever it is the harmonical oscillator, and we know the solution of that exactly. It's some combination of trigonometric function, so in general, the solution as a function of t is going to be a combination of this harmonic, some cosine and sine. I'll come back to this in a second. But you see the beauty of this, because now essentially you can discuss any kind of potential that your system may have, and as long as you are close to the equilibrium points, you are going to find the solution in terms of harmonical oscillators. Okay, so that's why the harmonical oscillator is very important, and in fact you find it everywhere in physics. Okay, it can be the effect. Since this then you try to apply this solution to any system. The first time you try for the system that you are interested in, and if it works, it's fine. If it doesn't work, maybe you solve this as the first order, and then corrections come in as perturbations, they are called, because you understand that if you go a little further away, then maybe these other terms that you are neglecting become large enough to change the solution, and so you start doing this perturbation theory about the exact solution. But this is a very good starting point, because at least you know this solution. So what I want to do is to study a little bit more about this differential equation, and also some equations that maybe you have already met or not, that are variation of this equation, of which we still know the solution, okay? Because this is the basic harmonic oscillator, but there are small things that I can add in here and still find an exact solution, or almost, and they make the problem even richer. So first, I want to So this is the usual way that I guess you are used to write a generic. So this is what is a differential equation, right? So let's just step back for a second from the physics and just look from just at the mathematics of the problem. This is a differential equation of the second order, right? With a constant coefficient and is homogeneous. Okay, this is the complete definition. And so the solution of this equation is a combination of a trigonometric function with a weight C1 and C2 depending on the initial condition, obviously. But probably you have seen that you can always, this sometimes is rewritten in terms of a single function. You can always rewrite this by using, right? You can always rewrite this as a single trigonometric function with a certain phase. This is called the phase. And this is called the amplitude, right? I mean, here you have, just think, right, you just call these constants here, you just name them. They are constant, but now you reshift them. You call this the cosine of alpha, that alpha, and this the sine, and this the, actually minus the sine of alpha. I can always do that. And then you use the nice combination, right? Well, actually, this could be larger than 1, so you should put a common factor like this, okay? Then you see that by using A comes from here, then you have a cosine of omega t, cosine of alpha minus sine of omega t, sine of alpha. That is also known as the cosine of this, from the same. And you can invert this, and then you can write always the amplitude is just, right, just by looking here, is just the C1 square plus C2 square, if you ever want to go back to that expression. And the tangent of the phase is just that ratio, right? So it's just minus C2 over C1 with this notation. So actually this is a nicer way. I mean, it's not nice to carry two functions. This is more compact. And this is the, is the oscillation, like the pendulum. And it's nice that here you have the amplitude and the phase. So the phase essentially is where you start. Then you start moving, right? And the amplitude is how big is this. And by construction, you want this amplitude to be relatively small if you want to stay in the small oscillation limit. If the oscillation is not small, for the case of the pendulum, I forgot, did we discuss that or not? Probably not, but I mentioned anyway that in that case you have a more complicated problem. Still, that can be solved exactly in terms of those elliptic functions, if you remember. What is the energy of this system? Well, the energy is this quantity, right, plus k over 2x squared, or by using this omega notation, I can factorize the m over 2, and then I simply have x dot square plus omega square x square. This is the energy. If I plug in my solution, I can compute the energy. Of course, the energy must be is the energy conserved in this system or not? Must be conserved. So it must be a constant. And in fact, if I plug in, you see this depends on time. But this combination is a constant. When you plug in the solution, you see that first you have the sine here, right, omega, right? You take the derivative, so you get the minus omega A omega sine of this, plus, you see, omega this with the cosine, so sine and cosine sum up to 1, and you drop the time dependence, and you have m over 2, and simply you have omega square, a square, by the sum of these two terms. So indeed, it's a constant. It depends only on the angular velocity, so the higher the frequency, the higher the energy, just like light, that is another harmonical oscillator, clearly. The higher the frequency of light or of your pendulum or of your spring oscillating, the higher the energy, and clearly the larger the amplitude, the larger the energy. So that's fine. This is the energy of this system. In fact, the energy is proportional, this is relevant, to the square of the amplitude. So it grows very fast with the amplitude. So a pendulum that is oscillating with very small amplitude has much less energy than the one that is moving back and forth like this. And the energy is completely conserved, so you have that nice experiment that if you have a very big pendulum, you drop it from 1 millimeter from your nose, it swings back, and then it comes back to you. It looks like it's going to hit you, but it cannot hit you because it started out here. If it hits you, that means that it's gaining some energy, right? So that always scares people a lot, because you see this big ball going, and then it's coming back very fast. But it must stop. So your faith in physics should allow you to stay there without moving, because you know that unless energy is not conserved, that is not the case, it will never hit you back. Very few people can stand this. It's really frightening. But that's the power of physics. Okay, actually, very often you will see that is even more it's even more convenient to rewrite this in a 1, 2, and a third form. That by you see, this is the cosine of omega t plus alpha. If I think as this as a complex amplitude, right, I can always write this quantity as the real part of a complex amplitude e to the I omega t, right? Where this complex amplitude is just my usual amplitude, the real quantity, time a phase that is exactly this. Because you see that if you multiply that and then you take the real part, you are back here, right? But this is a very compact form, right? Because I just have this exponential, and in fact the exponential is it's a very convenient function. It's much more convenient to work with the exponential in complex, on the complex plane, rather than having to do with the trigonometric function. And this, I mean, you know that e to the z is equal to, sorry, right? So by using this very impressive equation, in fact, if you put pi, right, you have one of the most beautiful equation of, because here you have all the interesting, you have the imaginary unit, the pi, the e, you have the three most important numbers in mathematics, all in one formula, and it comes from here. So if you have trigonometric function that we are bound to have, since we are discussing the harmonical oscillators, I rather stick to this complex notation that is more compact, and then, I mean, at the end of the day, I take the real part, and I'm back to the real world. Okay? So that's A bar is called the complex amplitude. Okay, so let's start with the first. So this is the harmonical oscillator. Essentially, I've told you everything you need to know, because this is the solution. These are various ways to write the solution. You have the energy, you have the Lagrangian. I mean, that's all. I mean, it's beautiful, we know the solution, but there is not much more than we can do, except look for problems, systems that can be described by that. I already say the spring, the force with the spring, the pendulum, atoms, light. I mean, there are many, many systems. You know, it's the case that you look, you know, well, if you have a hammer, I mean, everything looks like a nail. You look for systems that can be described by that. So how can I make things a little more interesting? So let's go back. So this is the solution. Let's go back to the Lagrangian and fiddle a little bit with the Lagrangian to a little bit of a generalization. So this is the free, what is called a free harmonical oscillator, and that was the solution, okay? One first, so I have just time to, let's do the first generalization. You see that maybe I would like to, so this had this solution. It's as I say, it's a homogeneous differential equation, and so that's why it's called the free harmonical oscillator. So it's freely oscillating under the influence only of its own potential. But clearly, the next level of abstraction would be what happens if I have some, say, your pendulum oscillating happily back and forth, nothing's going on, it keeps on going, but then I start hitting the bead sometime, right? So I'm, if you want, so clearly this means that I have, here is not zero, because this is the acceleration, right? So that means it's not just the acceleration proportional to the displacement, because there is the acceleration because of the displacement, but also I hit the bead with my finger, for instance. And so that means I introduce here a force that I call F, and let's assume that this is a force that depends on time. I'm going to then specify what time dependence. And you see, because of the dimensions, I have to divide by m. Always check your dimension when you write an equation. So that's a general situation. I have a free harmonical oscillator, and then I have an external force that is hitting the bead sometimes no, I don't know. But clearly, the most interesting, or maybe I should say, the case for which I still know the exact solution is if this, actually this force is not an arbitrary function of time, but is some trigonometric, some cosine, right? So I'm hitting with the periodically, but so I write this as some amplitude, and then a cosine, but I'm hitting periodically, but the frequency of this doesn't have to be equal to omega, right? Because otherwise it would be boring. So I write it in this form here, okay? So this is the external force, has some amplitude, some frequency gamma, and then it starts from some arbitrary position depending on the initial condition. So this is going on, and then periodically I'm hitting. So sometimes I hit, sometimes it doesn't. You know, sometimes you hit it while it's coming toward you, sometimes you hit it when it's going away. Can I solve this equation? Well, first, how does the Lagrangian look? How does it look like if you want to introduce this force? Okay. Well, you understand that if you want this extra term here, you have to add to your Lagrangian a terms that, you see, this comes from a derivative with respect to your generalized coordinate, right? And then that depends on time. So all you need is, you don't want this to come into the velocity, right? So it's just an extra term plus x, this f of t, right? Because when I take minus the potential, so I add this to the potential, now the potential is made of this. When I take dx, I get this extra ft that goes on the other side. Minus, plus. And then the m comes from the double derivative. So this Lagrangian gives you this differential equation. And now, what is this? This is, again, a second order differential equation. But now it's not homogeneous any longer, because I put by hand this extra term. And you know that a inhomogeneous differential equation of this kind has a solution that is the sum of the solution of the homogeneous one plus a particular solution of the inhomogeneous one. Did you remember this? That's a nice feature, because the homogeneous you know how to solve. Then you only need to find one solution for the other one, and then you have the general solution. So, I mean, so how do you solve this kind of, so this is the differential equation I want to solve. Well, usually you solve it by putting a test, I mean, the general one I know is the usual solution. What would be the, well, I mean, so the solution is the homogeneous plus a particular solution, let's call it x1, of this full equation. Well, clearly, if I can write a generic, I mean, it's periodic, so it must be a periodic function, so it must be a cosine. The only thing I don't know is what is the amplitude. And I try to find a solution that has the same frequencies than the perturbation force. So I look for a particular solution in which is in this form here. And you see that this is actually a solution, right? Because if you plug it in, you see that if B is F, that is this thing, divided by M, the difference of the square of these two frequencies, if B is this, then the solution, the full solution, that is this, that is A, the amplitude, cosine omega t plus alpha, this is the solution, the homogeneous equation, plus this particular solution, you plug in this in here, you see that this is a solution of the inhomogeneous equation. So we have found that so this is another problem that we know how to solve, because we have put this particular force that is simple. It's a periodic external force when you hit the system, and then you have this solution. And you see this is a nice solution. It's the usual one plus this particular solution. They are both periodical. And the only point that needs to be discussed, if you wish, is remember what I said the first day. Once you have your solution, you should look for particular cases or limiting cases. And we start out with two frequencies, right? The free motion frequency or angular momentum that I call omega, and the frequency of the external force. Now I look at my solution. I assume that you verify that this is actually the solution of this. And I ask, okay, if omega is different from gamma, nothing, you see, you have this term with a certain amplitude, so it's whatever it is. It's a combination of two oscillatory motion. But what happens if I'm hitting the system with a frequency gamma that is exactly equal to the free frequencies of the system? You see, it looks like it's blowing up. In fact, you can expand this, right? You can expand, add and subtract, and you see that this term grows with time. So what's going on? Is this, I made a mistake? I mean, you have to ask yourself, if you find a solution with an infinity, you know, in the real world there is no infinity, it's an abstraction, something that, so if you have infinity, but there must be an error, mistake. But let's just think, no, let's take again the system. This is a pendulum. So think of your little sister on a swing, and is swinging happily. She likes that very much. And then you say, she wants to be pushed. And the pushing is you, and it's this force, right? This is exactly this problem. It's a forced, it's called forced, because you are pushing your little sister. A forced harmonical oscillator. So there she goes, swinging, and you push. Now you know that if you push randomly, sometimes your sisters will come toward you. So when you push, you are actually slowing the swing down, right? Because it comes this way, you push. So actually, sometimes it's going away, and you push, and so then you increase the motion of that. If you are clever, in fact, this is the natural thing to do, that you push exactly with the same frequency of the motion. That is, when your sister's up here, you push. And when it comes back, you push. And what happens is that the amplitude keeps on increasing because you are pushing, you are putting energy in the system. And in principle, if there is no damping, this is the next thing that maybe on Friday we will discuss. If there is no damping, you really are shooting your sister, away. That is really infinity, because you keep on putting energy. This thing is not dissipating anything. So at a certain point, your sister goes around, and then okay, you are in trouble. But you see, so this is not crazy. The mathematics is telling you what is going on. It's simply the fact that you get infinity here is simply because this is too simple a modelization of the system, because clearly the swing is dissipating energy, right? There is air, is rotating at the hinges, so there is some friction, and so this cannot be the whole story. This Lagrangian is too simple, and because it's too simple, you get this infinity. But you understand why it's there. I mean, it makes perfect sense. So the next thing we want to do, in fact, let's start, and then let's start, and then we finished on Friday. As I said, so this was the forced harmonical oscillator, but you see that it's too simple-minded the system. I want to do one step further and make a more realistic system. And to do that, I first forget about the external force, so one thing at a time. So this was the solution that we got. So I raise again the external force. So I'm back where we started. But I want to introduce now not the external force. I want to introduce this damping. Now, the fact that there is friction around. And how do I do that? Well, you understand that, so let's work directly on the equation. Okay, then you can write the Lagrangian. So clearly I want some damping, and damping typically comes from, so it's proportional to the velocity, right? So what you want here is a terms proportional to the velocity. And usually this is written like this. You put maybe plus, let me put a 2, you see why I put a 2. So essentially a constant times the velocity plus your omega square, that now I call naught to remember that this is the frequency for a free motion in a way. So this is the differential equation for what is called the damp oscillation. Because I put here a frictional force that is damping the motion, so it's not free any longer. It has to face the fact that around in the real world there are many frictional forces, and these they go like the velocity usually. So you can remember that this is the free frequency. So remember, this is k over m, where k is the strength of the potential. And if you want, this 2L comes from well, this is a coefficient. So the force here goes like alpha the velocity, okay? But I put the 2. You see in a second why. So is this a differential equation that you know how to solve? Is this really, from the mathematical point of view, is this different from the previous one? Well, yes, because it has also the first derivative, but it's still of the same family. You remember this very large family of differential equations with constant coefficients, right? And those you know how to solve. That's the nice things. I mean, it doesn't matter. As long as these are constants, you know how to solve them. They are even simpler than the one we discussed before, because that was not a constant coefficient. So we had to find this particular integral. And sometimes, if this function is complicated, you are not able to find the particular integral that gives you the general solution. But if it's like this, so homogeneous differential equation with constant coefficients, well, in this case, second order, you know a recipe that tells you that the solution is very simple, because the solution is in this form, right? It's some combination of exponentials, where the coefficient here is given by the algebraical equation that you get here when you replace this equation here. Do you remember this? Did you do that with Narayan? No? Okay. But you remember that from somewhere. Anyway, you don't have to remember anything. I'm just telling you. You take this solution, you plug in there. If you take derivative of this, you just brings down, this is the nice feature about the exponential, right? Any kid knows how to take the derivative of an exponential, because it's just the exponential back, and you just remember this. So this leads to the characteristic equation, right? Because here you have two derivatives, so you get r squared. Here you have 1, so r squared 2 lambda r, right? Plus no derivative, so simply omega naught square equal to 0. So you replace a differential equation problem with an algebraical problem that clearly is simpler, because this is a second order algebraical equation that people knew since the Middle Ages, the solution of that. Up to what power here do we know the general solution? That's another interesting point, right? Algebraical equations, that was the same problem. You know, before they discovered derivatives, they play only with algebraical equations. So a linear equation, you already know the solution, right? It's trivial. Quadratic equation, it took time, but people, you know, discovered that the solution is always, you have two solutions, and they are given by minus half of this, minus lambda, plus minus the square root of the square of b, right? Minus, well, minus AC, but okay. So if you had the cubic equation, do you know the general solution of that? No, the exact solution. Well, indeed, yes. I mean, for the cubic, for the fourth order, yeah, fifth, no. What? What is Laplace? For the fourth order? What is Laplace? No, but this is an algebraical equation. It's a number, the solution. It's not a function. Okay, you show me next time. But okay, the point is that seventh order, there is no general solution, right? Of course, there is a general solution in complex space. Complex space, n polynomial has n roots, right? But not in real space. It goes up to the fourth order. But it took many years to discover. People really thought that you could find. So, you know, they really tried to find the solution for the fifth order and sixth order. It's like Fermat problem, okay? Actually, it's not trivial to prove that you don't have a solution. That took, it was done in 1800. Anyway, for us, it's just a second-order equation. So I know that the two roots are this, and therefore my solution, the general solution, is a combination of two exponential, like with some coefficient, the amplitude depending on the initial conditions, and you get these two roots. So e to the, I don't know, r1t plus c2 e to the r2t, where r1 and r2 are the roots of this characteristic equation. But now, so let me just finish this, and then you see that there is an interesting point here, because depending on the relative size of your lambda, that remember is the strength of your damping, the frictional force, and and your omega naught square, you may, I mean, this can be real or not, right? Because the square root, this has, so we really have two families of solution depending on whether lambda, so if lambda, I mean, this, say, is smaller than omega 0, or lambda is bigger than omega 0, right? Because you see that if this is the case, this really becomes imaginary, right? So I should write it like this. I have my solution in this case, right? So let me write it with a real. This I like it better. It's some amplitude that is given by a combination of these two. Then is the real of e to the minus lambda t plus I. I pull out an I, and then I switch the sign, so that I have the square root of omega 0 square minus lambda square t. Right? This is the solution. If this, are you following me? I mean, this is the general solution, R1, R2. If lambda is smaller than omega 0, this is negative. So let me pull out a minus 1, square root of minus 1, that is known as I, and then I switch this over in such a way that it's positive. So I get this term is always the same, and then I have I something, okay? So what is these things? I have to take the real part. So the real part of this is the real part of that, let me call it little a, that is the physical amplitude. The real part, this is a real function, so the real part of that is just this. And then the real part of e to the I, you just use Euler formula, is the cosine of omega t plus alpha, okay, where this omega is the square root. Sorry, minus. Okay, so I introduce a new omega because after all, this is some frequency. It's not the original frequencies that you had here. It's shifted by this lambda, okay, in that form. And so how is this solution? I can draw it because it's a one-dimensional problem. So here I have time, and here is my x of t. And you see what's going on here. It starts out, right? You see, I have this is damping. So it starts out oscillating. So it oscillates. It oscillates with a frequency that is omega, that is not, as I said, omega naught is shifted by a little amount. But the important thing is that it's not oscillating. While it oscillating, is damped by this exponential. So these two are an exponential like this. So it's oscillating like this and becoming, the amplitude gets smaller and smaller. This is exactly what you expect from a damping, right? Because you have your pendulum, but because of the frictional forces of the air, the amplitude doesn't stay the same as it should. some is dissipated, and so at the end it stops. And that's exactly what is going. It's oscillating, but as t goes on, then it stops because of the frictional forces. So this is the first solution. This is called under damping. Why? Because there is damping, but it's not so strong. The system has time to oscillate many times before it eventually kills off. What about this case here? This case is that everything is real here, right? So the solution, I can write it, is just the combination, C1 e to the R1, so minus lambda plus square root, right? Plus square root, so I can write it like this. T plus C2, right? C2 minus lambda plus square root of t. Whatever it is, you see, there is no oscillation here because the exponential oscillates only if it has an imaginary phase, right? If there is no imaginary phase, this is some combination of exponential where x of t in time simply goes like this. It doesn't have time to oscillate because it's so damped. In fact, this is called over damping. It's so damped that it just goes once and then it stops. Okay? So we have again a nice picture that corresponds to our physical intuition and is described by this very simple equation. Now you can I think I'll give you as an exercise. In fact, I give you two, or maybe I'll give you, well, I'll give it on Friday. So the exercise is simply, I want now to put back together the damped and the forced, as we say. Think of your system on there and find the solution. Okay. So this is the problem. I'll give it to you on Friday together with the problem, because now what is left is we have discussed the one-dimensional problem. So what happened when I have more degrees of freedom? I still want to discuss a system with many degrees of freedom that is oscillating, small oscillation, but now in several directions. So I have to develop a technique to find this, how the solution can be discussed, and that we will do on Friday.